This video is on gas stoichiometry under standard conditions. So we talked about in an earlier lesson that gases under standard conditions, we do have a shortcut for the ideal gas law. So standard conditions are a temperature of 273 Kelvin and a pressure of 1 atmosphere or its equivalent. And we found that at STP, all gases have 22.4 liters per mole. So this becomes a very handy shortcut for the ideal gas law, but it only applies at STP. And it says that there are 22.4 liters is equal to 1 mole of any gas. And since we do make a lot of measurements at STP, this comes in really, really handy and can save you a lot of work and time. So in the homework, we saw where we could convert from liters to moles at STP using this conversion factor. Here I kind of switched it around, and in this one we have moles of nitrogen monoxide for an experiment, and we want to know what volume of nitrogen monoxide would I need at STP. So for this one, what we're going to do is we have 0.0580 moles of NO, and we want to go to liters. But since it is at STP, we can use 22.4 liters per mole. So mole is here, mole has to go here, and in 1 mole there are 22.4 liters of any gas, and we're still talking about NO. So moles cancel out. All I'm left with are liters of NO. Move some of that sunshine. And I end up with 1.30 liters of NO. Everything on top multiplied together divided by everything on the bottom multiplied together. So again, you could do this problem and with the ideal gas law, have this as your N. Your standard temperature would be 273. Your pressure would be 1 atmosphere, and your R value would be the 0.0821. And you could solve for volume. But this way is a whole lot less work. But again, you can only use 22.4 liters per mole on a when it is at STP. So now let's layer in gas stoichiometry. Now, the good news is there's no new math here. We've done stoichiometry before, and so we have the process is going to be exactly the same. The same guiding question of can I use mole ratio? Because mole ratio is the only way to move from one thing to another in a chemical reaction, and it is based on the coefficients of those substances. Since it is going to be at standard temperature and pressure, you will be using the 22.4 liters per mole somewhere in your dimensional analysis. So we're going to start with this one, and it comes with a balanced chemical equation. If it was not already balanced, you would need to make sure that you balance it first, but this one's kind of a whopper. So I went ahead and balanced it for you. This is not a misprint. This is a this is a complex ion, which does happen, but it's kind of beyond the scope of this course. We're just going to use the balanced equation. So this question says, what mass in grams of aluminum would be needed to produce 4 liters of hydrogen gas at STP? Because it says STP in the problem, I know I can use this conversion factor. All right. So first thing I'm going to do is kind of make my map and without rewriting the equation. So we want to know what mass of aluminum, which is right up above it, would be needed to produce 4 liters of hydrogen gas at STP. So since it is at STP, I know I can use 22.4 liters per mole. All right. So first thing I'm going to start with is the number they give me in the problem, 4 liters of hydrogen. making sure to write down my units and my identifier because that's what dimensional analysis is all about. And then I'm going to ask myself the guiding question of, can I use mole ratio? That's going to help me decide what needs to happen in each of these situations. All right. So I have 4 liters here, and I want to ask myself this guiding question: can I use mole ratio? The answer is no, because I have liters here. But I have to use mole ratio to move around in a chemical reaction, to go from one thing to another. So I need to get liters to moles. And since it is at STP, I can use this conversion factor to do that. Liters are here, so liters have to go here, and there are 22.4 liters in 1 mole of any gas, and we're still talking about hydrogen gas. Now I have moles of hydrogen gas, and I go back to my guiding question: can I use mole ratio? The answer now is yes, because I have moles here. Now, when I do stoichiometry and I get to mole ratio, I like to lead with my units. So moles of hydrogen are there, so moles of hydrogen have to go here, so they cancel out. And then it's always moles of where you're coming from to moles of where you're going to. And so in this case, we're going to aluminum. That's what the question's asking about. Then we're going to fill in the numbers. The numbers are our coefficients. The coefficient for aluminum in that balanced equation is 2, and the coefficient for hydrogen is 3. Moles of hydrogen cancel out. Now I have moles of aluminum, but they don't want moles of aluminum. We want grams. So to go from moles to grams or grams to moles, I need to use my molar mass. And the molar mass of aluminum is 26.98 grams per mole. So that means there are 26.98 grams is equal to 1 mole of aluminum. Mole is here, mole has to go here, and always with molar mass, it's in 1 mole, there are this many grams. All right, and this is of aluminum. Everything on top multiplied together, divided by everything on the bottom multiplied together in one set of parentheses, I end up with 3.21 grams of aluminum. I want to match the same number of sig figs that I started with. And that's how you use this 22.4 liters per mole in stoichiometry to either come from volume and convert it into moles, or you could do it the opposite way and go from grams and actually convert it into volume of what you're going to produce. So I'm going to run through the same sort of scenario that I had here. But I'm going to show you a different positioning for this 22.4, because in this case, we started with liters. What if we start with grams? So I'm going to show you that here real quick. So in this case, or this practice problem, I've got 3.21 grams of aluminum. And the question is, how many, that's a question mark, how many liters of hydrogen gas am I going to form? So I'm going to start with the number they give me in the problem with its units and identifier. And I'm going to go through the same process here with stoichiometry. So it is, I have 3.21 grams of aluminum. And so I go to my guiding question: can I use mole ratio? Well, I have grams here, so the answer is no. But I need to use mole ratio because that's the only way to move around. So I'm going to use molar mass to convert from grams to moles. Gram is here, gram has to go here, and there are 26.98 grams in 1 mole of aluminum. Grams cancel out. Now I have moles of aluminum. I go back to my guiding question: can I use mole ratio? The answer is yes, because I have moles here, so do. Again, lead with your units: moles of aluminum to moles of hydrogen. It's always where you're coming from to where you're going to. We're going to fill it in with the coefficients. from the balanced equation. Now I have moles of hydrogen, but they don't want moles of hydrogen, they want liters of hydrogen. And since it is at STP, I can use this conversion factor to go from liters to moles and moles to liters. Mole is here, mole has to go here, and in 1 mole there are 22.4 liters of any gas at STP, and we're still talking about hydrogen. Everything on top multiplied together divided by everything on the bottom multiplied together into one set of parentheses. And if you do that, you're going to end up with 4 liters of hydrogen gas would be produced. So again, in this case, the 22.4 liters was our last step. And in the first dimensional analysis example, the 22.4 liters was kind of our first step. So it's going to go in one of those two spots with a mole ratio there in the middle.